we want to talk about DeepSeq. Now, in the last video, we have seen that seq can be used in order to evaluate to weak head normal form, meaning evaluating some data structure up to at least the first data constructor. But we have also seen that not only is there a weak head normal form, but also a normal form. And that normal form means that the whole data structure is evaluated. But we haven't seen how we can force this evaluation. And that's what we are going to see today. Now, in order to do this, we need to import the module control.deepseq. And before we talk about the theory of how this will work, we should look at the documentation of this module. Okay, so here we are in the documentation of control.deepseq. And this is also where one question gets answered. Why do we actually need this functionality in a lazy language such as Haskell? Well, think about this example, where we want to open a file, get its contents, and then close it, and after that return the contents of this file. Now, this might be something that you need within your programs. You might need to open files and then close them again all the time. The question is, when do we get the contents of this file? And that is a very important question, because if we do not really evaluate this S here and return it, it might not actually be the contents of the file, but a thunk pointing to the operation of getting the contents of this file. But the problem is that we want to close the file within this function, or within this IO action. So that's a problem. And this is where DeepSeq comes in. Now, DeepSeq works just like seq, which evaluated to weak head normal form, but DeepSeq now evaluates to normal form. Okay, so DeepSeq, as we can see here, works just like seq, but it needs some data type from the NF data type class, which we will look at in a second. Now, we've seen that there is an operator, an infix operator for seq. There is also one for DeepSeq. And then there is this force function, which is really nice, which is defined as x DeepSeq x, meaning x is being fully evaluated and then also returned. This is a very nice function. Okay, so now we are looking at the type class nfData, standing for normal form data. There is one method we need to implement for this class, which is RNF, and RNF will reduce the argument to normal form. This is important. It returns the empty tuple, but it has to evaluate A into the normal form. And that's about it. That is everything we need in order to have this nfData type class. Of course, what DeepSeq will do is it will call RNF in order to deeply evaluate this NF data. Okay, so let's look at some instances. Now, bool, chars, doubles, so any numbers that we can have are in this type class. Also void and the empty tuple. And then also, let's see, where can we find it? Also the lists, if the lists contains, of course, some NF data. And then also stuff like product sum, first, last, maybe, of course, the standard things. Also either is in this type class. So yeah, and also a lot of tuples. So with a lot of the data types that we have already seen, we can do some deep evaluation. It is very important to understand that seq can always be used. That is just something that is basically built into Haskell. But the DeepSeq cannot always be used. That is very important. Okay, so let's look at some examples. Okay, so here we are on GHCI, and we want to take a look at DeepSeq. So we can import it, and now we have the DeepSeq function. So let's create a data type that is in the nfData type class. So maybe a list of ints. Of course, we can use sprint in order to get the unevaluated view of this data structure. So in this case, yeah, it's just a thunk. Now, if we call seq on it, we have evaluated to weak head normal form. And now let's try DeepSeq And here we now have a fully evaluated list. So DeepSeq did just what we expected it to do. Of course, this also works with a more, with a more interesting definition. So for example, we could map this A with some function again, and then of course we have the unevaluated B, which is unevaluated, and then calling DeepSeq on B will of course evaluate it fully if the types allow it. But of course the int and the list is in NF data, so it allows the evaluation. Okay, now of course we also have the force function, which can be used in order to do this evaluation. So let's go back, let's redefine A, and now let's use force, and force does, well, just what we wanted to do. But here's a little catch. So let's say we have our unevaluated A, and let's say we want to define something like B is force of A. Now what you might think happened here is that we forced the evaluation of A and stored it in B. But that sadly isn't true, as we can see here. So B is now an unevaluated thunk. Well, why is that? Well, that is weird, so let's maybe call sec on B and evaluate it to weak hat normal form. And now we see that it is fully evaluated, but we only called sec on it. So what is actually happening here? Well, it's very important to understand that if you call sec, DeepSeq, or force on any function, you just use it as a definition. So in this case, saying that B equals force A is a definition for B. But that doesn't mean that the evaluation is done right at that point in the code. What that means is that if we need to evaluate B, then it will be, it will have the definition of the normal form of A. So that's why calling sec on B actually resulted in the full list to be evaluated, because B is pointing to a thunk, and this thunk is telling the runtime system of Haskell to fully evaluate A. And of course, if this thunk is evaluated to weak hat normal form, this basically tells us that, well, it wants to evaluate it to normal form. So this basically elevates shallow evaluation to deep evaluation. So that's a little gotcha, and we will see in a later example why we need to be careful when using force and DeepSeq. But now one question we have to answer is, we have seen that NF data takes, we need to make it a bit smaller. NF data needs to have this RNF method. And the question might be, how would you define such a method for a completely new data type? And that's something we want to take a look at right now. Okay, so here we are in a little example program where I defined the Peano numbers. So how they work is you have a 0 constructor pointing to 0, and then you have a successor constructor telling you that this is the successor of this recursive Peano number. We also have a little add function here that we will use later, and we already have a predefined 5. So this is how it works. This is the successor of 0 and its successor, and the successor of that, and the successor of that, and the successor of that, of course. So this is a way of defining every natural number there is. So now the question might be, if we want an instance of NF data for this, how do we define RNF? Well, let's do some pattern matching. If we have the 0 constructor, we are already finished, because there is nothing that we still need to evaluate, of course. Now it's interesting, what if we have the recursive constructor for the successor? So now we have this recursive data structure A, and A might not be evaluated. So we have to force its evaluation. How do we do it? Do we use sec on it? Because we cannot use DeepSeq. DeepSeq would use RNF. So how do we do it? Well, in this case, we can actually do a little trick, and just call RNF recursively. Why does that work? Well, it actually evaluates the whole data structure just by pattern matching. So, assume that we want to evaluate 5 here. So 5, right at the beginning, is a thunk. For the first pattern matching, we have to evaluate the first constructor. So we get the first constructor out of 5, and then we end up in this function definition where we do the recursive call on A. So A in this case is everything that is left in 5. So we do the recursive call and evaluate the next constructor. And after that, we, evaluate every constructor recursively until we end up with 0 in this case, where we return the empty tuple. And then we have fully evaluated this data structure. Okay, so let's look at that in action. We will start up GHCI and use this module. So we have already seen the definition of 5. So 5 in this case is a thunk. And now let's call DeepSeq on it, because that is now totally possible, because NF data now has an instance for our Peano numbers. And now if we take a look at it, we can see that it is fully evaluated. In the last example, we had an easy task of defining RNF simply because the recursive nature of Peano numbers allowed us to have a clear recursive path. But what if we have a tree where this path is not clear anymore because there are 2 paths for every node that we visit? So here we have a problem of defining RNF. Okay, so here we have the data type for a tree, and we have defined an insert function for it, and here we have a data variable that we will play with later. How do we define RNF? Well, RNF for a leaf is of course trivial. That is already evaluated. But what if we have a node? Now observe that this node has a left subtree, a right subtree, and a value. The value itself needs to be evaluated, so this is why we need to have a prerequisite of saying that the actual data type that is within our tree also has to have an instance of NF data. Okay, so if we have that, the actual definition looks like this, where we have recursive calls to RNF for the left and the right subtree, and we force their evaluation with sec. So this is interesting, right? Why do we use sec for this? Well, let's look at RNF of V. This RNF is not the RNF we're defining right now. It is the RNF that comes from this instance. And its definition tells us that if we want to evaluate RNF, then this forces this thunk to fully evaluate whatever V is. So calling sec on it, just as we have seen before, is totally fine. Because sec, forces the evaluation to weak hat normal form. But the definition of RNF tells us that even if we want to evaluate to weak hat normal form, this is totally fine because it forces the evaluation to go deeper. Shallow evaluation is then, promoted to be deep evaluation. And that's exactly the theory we have behind RNF of L and R. So observe that the recursive nature of RNF tells us that RNF will fully evaluate the left subtree. How does it do it? Well, by the recursive definition here. So if we want to evaluate RNF of L, we have to go into the definition of RNF again, which is, of course, this function. This is recursive. So for the definition of RNFL, the left subtree of L will be evaluated because we are calling it with sec. And sec tells us that at this point we force the evaluation. This is very important. Okay. And of course we do that with V and we also do that with R. This is why sec is so helpful and why the definition of sec is so helpful, because this basically allows you to chain different recursive parts of your RNF definition, which is really nice. Okay, So that is how RNF is defined. It might be a bit hard to get your head around how this actually works, but just keep in mind that the definition of RNF tells us that shallow evaluation, so something done by SEC, is promoted to deep evaluation by definition. And the definition comes from the recursive nature of RNF here. So let's look at this in action. So we will call GHCI on this file, and we can look at the variable that we've seen before, the t, which basically is a tree which will be built by calling fold L on insert with a certain list. So let's use DeepSeq on it. And as we can see, yes, the whole tree was evaluated. Okay, so we now have seen how we can define RNF for different data types. The question really is, when is the actual evaluation done? So as we've seen before, forcing the evaluation of a value, like b equals force of a, might not yield the result that we want. So now in the last example, we want to take a look at how to use this in a real program. So here we are in an artificial program that just tries to demonstrate how evaluation works. So here we have something, which is a function, a pure function that does some computation. What that computation is, we don't really care. And here we have the IO action, which does the same thing, but it forces its evaluation with this little infix operator we have seen before in the documentation. So how do you force the evaluation of something? Now, we have seen that just calling force doesn't work, right? So something like let result 1 equals force of something, that doesn't work, because now result 1 is just pointing to a thunk which would force the evaluation if we actually wanted to evaluate this thunk. So this is where we can use evaluate. Evaluate is a function from control.exception. And the interesting thing is that this evaluate forces the evaluation of this thunk right at the point where we call it. So it creates an IO action from some data and then evaluates it. Why is this helpful? Well, it can be used in order to force certain exceptions to happen at a certain point in time. Imagine that you have some pure code that can throw exceptions. The problem is that if you store it as a thunk and you check for an exception at a certain point in time, this thunk doesn't get evaluated and then may be thrown at a much later point in time into the code, where it then throws an exception where we don't check for the exception anymore. This causes a problem because it's an uncatched exception. So this is where we can use evaluate in order to force exceptions to happen at a certain point in time. And we can reuse this function with force in order to deeply evaluate a result from a pure function. So you could write a function called full eval maybe that does a full evaluation of this x here. You could do that, but well, you might not want to, which we will talk about in a second. But the cool thing is that now result 1 is fully evaluated at this point in time, which is cool. What's much cooler is that something IO has the same behavior, but in a much cleaner and simpler style. This is due to this infix operator. We have seen this in the video on concurrency, where I have used the sec version of this. So I have used this version of it in order to evaluate something to weak hat normal form, in this case an integer, in order to have a computation ready in a thread. But you could also use the DeepSeq version of this and then fully evaluate something coming from an IO action, which is pretty nice. So let's look at this in action. We will load this file into GHCI. So let's store the result of something in A. And as we can see, it's not evaluated. And if we force its evaluation, we can see that it's still not evaluated because, of course, B is pointing to a thunk. So this is the point where we can use evaluate and evaluate of B now forces its evaluation, because now result is actually evaluated, and with that, of course, A is also evaluated. So this is how we can force the deep evaluation, which is great. Okay, so we have also seen that something IO does the same thing. So let's store something IO of maybe another number like 15 into result. And if we look at the evaluated view, yes, it already has been evaluated. So that is a very nice way of forcing evaluation. And it comes in handy if you want to control when certain things are evaluated. But that's the important thing. Do you actually want to do that? Well, when dealing with I/O or networks or something like that, yes, you do want to do that, because you want to interact with your environment basically in real time, as you might say. So this is where forcing the evaluation comes in handy. But for pure calculations, you might not always want to force evaluation, because if you have a definition like this, which is an infinite list, of course, forcing the evaluation of A in this case would, well, be an infinite loop, which is something that we do not want. So be aware of those limitations of deep evaluation. You can use it, and again, for concurrency, for example, it is very helpful, but it should not be the default way of handling data within Haskell. Haskell is a lazy language, so we should keep it lazy, because being lazy is not as bad as one might think. You wouldn't believe how many coffees I run through making one of these videos. If you'd like to support them, you can do so on Ko-fi, where you can, well, buy me a coffee. Any support is greatly appreciated. Thank you.